at the topics of the previous sessions. In previous sessions, we discussed about important discrete distributions for discrete random variable. We talk about Bernoulli distribution and y, that is a function of x. We want to compute the PMF or PDF of y. In the previous session, we discussed that if x is discrete, y will be discrete. And we discussed, and we have an example that when we have the PMF of x, how we can compute the PMF of y. If you have any questions from the previous session, please ask. Okay, let's go ahead. But now, for this session, we want to talk about PDF of y when x is a continuous random variable. Assume that x is a continuous random variable with PDF function equal to fx, okay? Or fxx. X is a continuous random variable and its PDF is denoted by fxx, this function. Okay, this function is PDF of x. Now, we have y. Y is a function of x, gx. Y is equal to gx, so y is a function of x. What we want to compute the PDF of y. We want to compute the PDF of y. What is the PDF of y? Okay. To obtain the PDF of y, we should start with computing CDF of y. Now I write the CDF of y. CDF of y, we use sample F for CDF. CDF of random variable y. At the point y, you know that it's equal to that or random variable is less than or equal to y. Okay, but we know the PDF of x. We don't know this value for y. So we should establish a connection between y and x because we know x and we don't know y. Okay, we know that y is equal to gx, so we replace this in this equation. We know that y is equal to gx. So the probability that the random variable y is less than or equal to a special value y is equal to this. Okay, but how we can compute this probability? From the PDF of x, we can compute this probability, but it's related and it's dependent to the form of gx. Okay, now we want to compute the probability that gx is less than or equal to y. We can compute this probability using the PDF of random variable x or CDF of random variable x. When we have PDF of x, we can easily compute the CDF of x. But it's dependent to the form of g, to the form of function g. Okay, let's see an example to more clarify this subject. For example, suppose that we have random variable x. Random variable x has exponential distribution with parameter lambda. It means that the PDF of x is such this for positive x, as we talked about it in previous session. Okay. At this example, we know that x is a random variable with exponential distribution. So the PDF of x is like this. Okay? Now, we know that y is a function of x and y is equal to x plus 2. Okay? Now, we want to compute the PDF of y. Okay, this example gives us the PDF of random variable x and wants to compute the PDF of random variable y that is equal to x plus 2. So y is a function of x. Y is equal to gx, and here gx is such this, is like this. Gx is equal to x plus 2. Okay? How we can compute PDF of y? As we mentioned in previous slide, first we should start with CDF of y. So we write the meaning of CDF of y. Okay, we want to compute this probability, but we should establish a connection between y and x. We know that y is equal to x plus 2. So probability that y is less than or equal to 1 means that x plus 2 is less than or equal to y. Okay? It means that probability that x is less than or equal to y minus 2. Okay, if we have a PDF of x, also we can compute the CDF of x. When we have PDF, we have also the CDF because CDF is an integral of PDF function. Okay, we now want this probability. Probability that x is less than or equal to y minus 2. We know that CDF function at every point means that the probability that a random variable is less than or equal to that value. So this probability, that is the probability that a random variable x is less than this value, is equal to the CDF of x at this value. CDF of x at this specific value y minus 2 is equal to this probability. Okay, now we obtain the CDF of y. CDF of y is equal to CDF of x at y minus 2. Any question from these computations? Okay. We obtain that CDF of y is equal to CDF of x at the point y minus 2. But pay attention that we want to compute the PDF of y. We have CDF of y and we want PDF of y. We should take derivative from CDF to obtain PDF. Okay, PDF is a derivative of CDF, so we should take derivative from CDF function to obtain the PDF function. So we should take derivative from this function according to y. Okay, and we can compute PDF of y. Okay, but how we can compute the derivative of this function? Please pay attention that when we have a composite of some function, assume that we have f gx. Okay, we have f gx, and we want to compute the PDF, and we want to compute the derivative of this function. Derivative. Okay, it's equal to f prime gx times j prime x. Okay, we have this formula to take derivative of chaining function, composite function, We have a chain of function, and the formula of derivative of f gx is equal to this f prime at gx and times j prime x. Okay, now we use this formula to compute the derivative of this function, to take the derivative of this function. So we know that PDF of y is equal to the derivative of CDF. Okay, so it's equal to, and according to this formula is equal to CDF of x, the derivative of CDF of x. Derivative of CDF of x is equal to PDF of x at y minus 2 times j prime x. J prime, we have j prime y here. Y minus 2. Y minus 2, if we take derivative from y minus 2, it's equal to 1. So the PDF of y is equal to PDF of x at a point y minus 2. Okay? I repeat the explanations of these examples. X has exponential distribution. We know that y is equal to x plus 2. We want to compute PDF of y. First of all, we find CDF of y. This is the definition of CDF of y. And we should establish connection between y and x, and we know that y is equal to x plus 2. So CDF of y is equal to this. And now we have CDF of y, and we should compute the PDF of y. So we should take derivative of CDF to obtain the PDF. And the PDF is like this. We obtain that PDF of y is equal to this. And we know that x is an exponential random variable with parameter lambda. So we replace the formula for exponential distribution here, and we have, so the PDF of y is like this. Because we replace this to obtain this. This is the PDF of y. Okay, any question? Okay, also we have another approach to compute the PDF of y. When we have y is equal to gx, we know the PDF of x, and we want to compute the PDF of y. Okay, we have another approach. What's this approach? This approach is using this formula. But what is this formula? Please pay attention. For simplicity, at first forget this summation and focus on this formulation. What's this formulation? We have fx. Fx means the PDF of x at a point xi. And we have absolute of j prime. What's j prime? J prime is the derivative of g at a point xi. Okay, this formula is clear, but what we should know is xi. What is xi? Okay? At the numerator, we have PDF function, and at the denominator, we have j prime. J prime. G is this function, and j prime is the derivative of g. Okay, we should discuss about xi. What is xi? Xi is such this. Pay attention. We have y is equal to gx. Okay. If g is an invertible function, if g is invertible, then we have the invert of function g as this function. Okay. Here we have the formula of y in terms of x. Here we have the formula of x in terms of y. Okay, x1, it means that in this formula, xi means x in terms of y. Okay, if g is a invertible function, then we have one xi, only we have x1. But if g is not invertible function, we may have some xi, for example, x1 and x2. In this situation, when we have x1 and x2, this sigma is important. But if g is invertible and we have only one xi that is equal to x1, we don't need this summation. Okay, let's see an example to be more clear. Previous example, y is equal to x plus 2. We know the PDF of x, just similar to the previous examples. We know the PDF of x and we want to compute the PDF of y. This formula, pay attention, this formula is like this. Okay, we know that fx is this exponential distribution. We should compute J prime. Now we have y is equal to x plus 2. So J prime x is the derivative of this function according to x. So it's equal to 1. Okay, but what's xi? Xi is the expression of x in terms of y. So here we have y is equal to x plus 2. So if we want to express x as a function of y, we have this equation. X is equal to y minus 2. This function is invertible, so we have only one xi that we call it x1. Okay, so here we don't have this summation because we have only one x1, we have x1. So from this formula, we can write the PDF of y very simply and directly. We have this formula. Fx at xi, it means that xi here is x1 as is equal to this. Here we have absolute of J prime xi. J prime x is equal to 1, so it's equal to. So we have fy or the PDF of y is equal to PDF of x at the point y minus 2. Previously, we had this formula, but from the first approach. Here, we directly use this formulation, and very simply, we can obtain the PDF of y. And if we replace the exponential distribution for fx, we have fx is an exponential distribution, and we replace it in this formula, and we have okay. From the first approach, we have this formula and we have the same formula from the second approach. So the second approach is very easy. You should use this formula and you know fx, you know J prime xi, only you should compute the PDF of y. So In these slides, we discuss about function of a random variable. We know random variable x and we know the PDF of x or PMF of x, and we want to compute the PDF of y. We have two approaches to compute the PDF of y. First approach is based on computing the CDF of y, and the second approach is based on using this formula. Um, for example, it's good that you discussed and you studied this example. Y is equal to x to the power of 2. Okay? We know the PDF of x. What's the PDF of y? What's the PDF of y? You can study these examples yourself. Here, if we want to express x in terms of y, we have 2. We know that x is equal to positive and negative radical y. Okay? So we have 2 x1 and x2. So here we have this summation. Okay? Let's go ahead. Here, we want to talk about mean and variance of a distribution. If we have a discrete random variable, the mean or expectation of this distribution is denoted by this symbol. Okay, this means expectation of x, or it means mean of x. For discrete random variable to compute expectation of x, it's enough to multiply each value by its probability and summing these values. For example, x takes the values, uh, for example, x takes the values negative 1, 0, and 1 with the probability yek 3. Okay? If we want to compute the mean of x or expectation of x, we should multiply each value by its probability and summing them. So we have this. That's equal to 0 for this example. Okay. But if x is continuous, this summation is changed to integral for continuous random variables. For continuous random variables, also we use this notation to denote expectation of x or mean of x, and it's equal to this. It's equal to the integral of x times fx, x times fx. So we should multiply x by fx. Fx here means the PDF of x, and we should integrate from negative infinity to positive infinity to compute the mean of a random variable. Okay, random variable or expectation of a random variable for discrete case, and here this integral for the continuous case when we have a continuous random variables. But the expectation has some properties. The first property is such this. It says if we have this equality, it means that if the PDF of random variable, if the PDF of random variable is symmetric around A, okay, then the expectation of random variable is equal to A. Okay? For example, if we have this distribution for a random variable, and here is the point 2. This is the PDF of a random variable. Okay? Suppose that the PDF is symmetric around 2. Okay? Uh, From these properties, we know that the expectation of the random variable with this PDF function is equal to 2. Okay? So if you have any PDF that is symmetric around a point such as A will be the expectation of that random variable. Or for example, this distribution. This distribution is symmetric around 3, so the mean of this distribution or the expectation of the random variable related to this distribution is equal to 3. Okay, second property. If we have y is equal to gx and we want to compute the expectation of y, or we want to compute the mean of y, we know that the mean of y is equal to this. To compute the mean of y, we should multiply y with its PDF and then integrating from negative infinity to positive infinity. But pay attention that we want the expectation of y, but we have the PDF of x. We don't have the PDF of y. Okay? We have y is equal to gx and we have the PDF of x and we want the expectation of y. We have expectation of a function of x. Here, it's enough to multiply gx by PDF of x and integrating from negative infinity to positive infinity. It means that if we want to compute any function of x, okay, any function of x, for example, sinus x, exponential x, for example, x to the power of 2 plus 2, any function of x. If we want to compute the expectation of any function of x, when we have the PDF of x, it's enough to multiply this function with the PDF and integrating from negative infinity to positive infinity. For example, if we want to compute the expectation of x2, it's enough to compute this integration. Okay? Again, I repeat that if we want to compute the expectation of any function of x, it's enough. If we want to compute this expectation when x is or random variable, it's equal to this. Okay? And now how we can compute, for example, e expectation of sinus x? We know from this property that expectation of sinus x is equal to this. Okay? Any question? Okay, so the expectation of a random variable or the mean of random variable that we denote it with this symbol is equal to this summation for discrete random variable and it's equal to this integral for continuous random variable. An example. Let's see an example. This example says us we know that we have a random variable x. Okay, we have a random variable x. We know that we uh, we know that probability that x is less than 0 is equal to 0. Okay, and alpha is a positive constant. Alpha is a constant and alpha is positive. We should prove that the probability that x is greater or equal to alpha is less than or equal to expectation x divided by alpha. Okay, again I repeat the example. We have a random variable x. We know that probability that x is less than 0 is equal to 0. So x is positive. X can't be negative. Okay, and alpha is a positive constant. We want to prove this inequality. Okay, let's start to prove this inequality. Let's start with the definition of Ex. We write the definition of E, expectation of X. We know that expectation of X is equal to this. From this slide, we know that expectation of X is equal to this. So we write this. Also, the example said us that the probability that x is less than 0 is equal to 0. So x is not negative. So the PDF of x for negative value is equal to 0. So this integral from negative infinity to positive infinity is equal to the integral from 0 to positive infinity. Why? Because PDF is equal to 0 for negative value. From negative infinity to 0, this PDF is equal to 0 because the example said us this. Okay, so we have this. But how obtain this inequality? Okay, please pay attention that here we want to compute the integral of x times fx from 0 to positive infinity. X times fxx is positive for all of the x in this interval. Please pay attention. X is positive because x is between 0 and positive infinity. Fxx is positive. Why? Because PDF is positive. We know that PDF is positive. So we can write this inequality. Let me again repeat this formula. Why this integral is greater than this integral? Because the function that we integrate is positive in the interval between 0 and positive infinity. And here we integrate from alpha to positive infinity. Okay? So here we have that this integral is larger than this because this integral is equal to this. Okay, we have this formula for this integral. I just write this equation from 0 to positive infinity, from 0 to alpha, and from alpha to positive infinity. Okay, you know that this integral is equal to this summation. Okay, and we know that this term is greater than or equal to 0. So this integral, that is the summation of these two integral, is larger than this integral that is this term. Okay? So we have this inequality. Now, also we have that for this interval, x are larger than alpha. So this integral is larger than or equal to this value. It means that we know that fx is positive and also x is positive. In this integral is between alpha and positive infinity. But in this integral, we replaced x with the constant alpha. So here x is between alpha and positive infinity, and in this integral, we replace x with alpha. So this integral is larger than or equal to this integral. And here, what's this? We integrate the PDF function from alpha to positive infinity. It means that the probability that x is greater than or equal to alpha. From the properties of PDF function, we know that to compute this probability that x is greater than or equal to alpha, if we want to compute this probability, we should integrate PDF function in this interval. So this equal to this. Now, now our proof is complete because we obtain expectation x is greater than alpha times we obtained, and we prove this inequality here. If you divide two sides by alpha, we have this inequality, and we prove the inequality that we want. Okay, any question? So in this example, we prove this inequality by using this information about the random variable x. Okay, sure. I repeat the explanation. To prove this, please pay attention. To prove this formula, we start with defining expectation of x. We know that expectation of x is equal to this. Do you have my pointer? Do you have my pointer? Okay. So, expectation of x is equal to this. The example says us probability that x is negative is equal to 0. So x is positive. It means that the PDF of x for negative value is equal to 0. So this integral from negative infinity to positive infinity for this random variable that is positive is equal to 0 to positive infinity. Okay? But now, we know that this integral, that we repeat this formula here, this integral is previously we wrote this, but now we don't have the formulation. We know that this integral from 0 to positive infinity is equal to integral from 0 to alpha plus integral from alpha to positive infinity. Integral from 0 to alpha is positive. So it's positive and it's equal to the summation of two integrals. So this integral is larger than this integral because this integral is equal to this with a positive value. So this is greater than or equal to this integral. Okay? And here, why we have this inequality? Because here fx is positive, also x is positive. In this integral, we multiply x by fx and compute the summation, this continuous summation. You know that integral is a continuous summation. We multiply x by fx and then compute this continuous summation. If we replace x with alpha, alpha is the smallest value that x has in this interval. If we replace x with alpha, it's clear that this integral is greater than this integral that we omit x and we replace x with a constant alpha that is the smallest value for x in this interval between alpha and positive infinity. So we have this inequality. But what's the meaning of integrating PDF of x between alpha and positive infinity, it's equal to the probability that x is larger than or equal to alpha. So here we prove the example, or proof is complete. Okay, any question? Okay, here we have some examples. Suppose we have this random variable x. This is the PMF of this random variable. This random variable takes the values negative one half and positive one half with the same probability of one half. Can you say what's the average or what's the mean of this random variable? What's the expectation of this random variable? What's the expectation of x? To compute the expectation of x, here x is discrete random variables. As we have in this example, we should multiply xi by the probability and compute the summation. Okay, x takes the values negative half with the probability of one half. And it's take the value one half with the probability of one half. As you can see, the expectation of these random variables with such PMF is equal to 0. Now, here we have another random variable. Also, we denote x for this random variable. Okay, this random variable takes the values negative 100 and positive 100 with the same probability of 1/2. Okay, what's the mean of this random variable? What's the mean expectation of x, such x? Can you say? Yes, it's equal to 0. Because to compute this, we should multiply negative 100, 1/2. You can see that the expectation of this random variable and this random variable are same, are 0. But these random variables are very different. This random variable take the values negative 1/2 and positive 1/2. But this random variable take the values negative 100 and 100. Okay, these random variables are very different, but their expectation is equal to each other and it's equal to 0. So we should define another definition for another statistics. We should define another statistics for a random variable that we called it the variance of random variable. Variance of random variable x is equal to this. It's equal to the expectation of x minus expectation of x to the power of 2. What's the mean of variance of x? Variance of x specify the dispersion, the spread of PDF or PMF around the mean. If variance is big, is large, if variance is large, it means that the dispersion around the expectation or around mean is large. If variance is less, is very low value, it means that the PDF or PMF are compact around the expectation value. Okay? So the variance show the dispersion of distribution around EX. Here in this example, dispersion around the mean, that mean is equal to 0, is a small value. But here, the dispersion around the mean that's equal to 0 is a large value. Okay? Also, we use this notation for variance of x, because variance is also positive. Variance of a random variable is positive. Expectation x or mean of x is not maybe positive, maybe negative, but variance is always positive. So we use this notation for variance, and here sigma is called a standard deviation. So a standard deviation is equal to radical variance x, and variance x is equal to a standard deviation to the power of 2. Okay, so variance of x specifies the spreadness and the dispersion of distribution around the expectation of x, around the mean of distribution. Okay, this is the meaning of variance. But what's the properties of variance? Variance of x is equal to this. Expectation of x to the power of 2 minus expectation to the power of 2 of x. The second property, if y is equal to ax plus b, here a and b are constant. Okay, a and b are constant. X is a random variable. We know that y is equal to a x plus b. Okay, if we want to compute the expectation of y, we should compute expectation of ax plus b. Okay, from these properties of expectation, we know that expectation is a linear operator. So, if we want to compute the expectation of y, it's equal to a ex plus expectation of b, and expectation of a constant value is equal to that constant value. Expectation of a constant value is equal to that value. For example, expectation of 2.5. Here we don't have any random variable. Expectation of a constant value is equal to that constant value, is equal to 2.1. Here a and b are constant, and we have this equation. Okay, but now in this slide, we want to discuss about the variance of y. What's the variance of y, and what's the connection between variance of y and variance of x? We have this equation. Variance of y is equal to a to the power of 2 times variance of x. What's the variance of v? Please pay attention that variance of expectation of a constant value, for example, just for example, 2.5 is equal to this value. But the variance of a constant value is equal to 0, because variance means the dispersion around the expectation, and the constant value has no dispersion. So the variance of constant value is equal to 0, and the expectation of a constant value is equal to that constant value. So here we should pay attention that if we multiply a random variable x by constant a, then the variance of y is equal to a to the power of 2 times variance of x. For example, if variance of x is equal to 3, variance of 2x, according to this formula, is equal to 2 to the power of 2 times 3. Okay, the variance of 2x is equal to 12. Okay? Yes. Here, this slide, you mean, Mr. Ahmad?
Yes, doctor.
Okay,
Yes, yes.
okay. If you have any question, please, here you are.
Return, doctor.
Okay, I again, I again talk about this slide. Here, we defined another statistics to work with random variables. Previously, we defined expectation of x. It means that mean of x, or expectation of x. But expectation of x don't give us expectation of random variables don't give us any information about dispersion of random variables. So here we defined variance of x. Variance of x has this formula, can be computed due to this formula. But what's the meaning of variance? Variance of a random variable such as x specifies the dispersion of the distribution of that random variable around expectation of x. Okay, so if we have a large variance, it means that we have a large dispersion around the expectation of x in our distribution. If we have a low variance, it means that we have a low dispersion around expectation of x in our distribution. Okay, so variance determines the compactness or spreadness of a distribution around the mean of this distribution. Okay, and here we have some properties of variance. This is an important property. If we multiply a random variable with a constant, then the variance is equal to this. Okay, here we have another property. You're welcome. If variance of a random variable is equal to 0, it means that probability that random variable is equal to expectation is equal to 1. It means that this is a constant value. Variance is equal to 0 if we are faced with constant value. Okay, variance is 0 for constant value. And here we have Chebyshev inequality. We don't want to discuss about this inequality because it's uh, almost complicated. Okay, forget this property. Only pay attention to these three properties of variance. Okay, let's see an example about computing the variance and mean of a distribution. Here we have what distribution? Here we have a distribution. Do you remember what's the name of this distribution? PDF function of a random variable x is such this. What is this distribution? What we called these distributions? What's the name of this PDF? We discuss about this distribution, this PDF here. This is a uniform distribution. Okay, this is the uniform distribution. In this example, we want to compute the mean of these distributions. The mean, the average of this distribution, EX. Okay, to compute expectation of X or the mean, of this random variable, we know that this random variable is continuous. So we should compute this integral. But as you can see from this plot, the PDF function is 0 and it's equal to this value only in the interval between A and B. Otherwise, the PDF is equal to 0. So, to compute this integral, uh, we have integral between A and B, x, and PDF. And here we should replace the formula for PDF. PDF outside the interval between A and B is equal to 0, and this interval is equal to 1 divided by B minus A. Okay? So we should compute this integral. How we should compute this? You know that the integral of x is equal to x to the power of 2 divided by 2. And we should replace A and B in this formula. Okay, if you compute this integral, the mean is equal to A plus B divided by 2. Okay, we can expect that the expectation or mean is equal to this, and it's not needed for us to compute this integral. Can you say that how we can guess the mean of this distribution expectation? How we can guess the expectation of these distributions without computing this integral? Pay attention that here we talked about this property that if the PDF is symmetric around a point, for example, in this PDF is symmetric around 2, so 2 is the mean of this distribution. Here the PDF is symmetric around 3, so the 3 is the mean of these distributions. Here the PDF is symmetric around this point. Okay? PDF, as you can see, is symmetric around this point. So without computing this integral, we can guess that the mean is equal to this value, A plus B divided by 2. Okay? Because PDF is symmetric around this value. From the properties of the expectation, we know that this symmetric A plus B divided by 2 is our mean. Okay, anyway, you can also compute this integral and obtain the mean as you can see in here. Now we want to compute the variance of x. Okay, we want to compute variance of x. We know that variance of x is equal to this. Expectation So we should compute expectation of this function of x. So we should multiply this value with the PDF of x. Why? Because we know that expectation of any function of x is equal to this. Okay? Previously, here, we discussed about this. Okay, we said that if we want to compute expectation of any function of it, it's enough to multiply that function gx by PDF and integrating. Okay, here we use these properties. And we know that to compute variance of x that is equal to expectation of this, it's enough to compute this integral. This is or gx here. Okay, so we compute this integral. Here we have gx, here we have fx, and we multiply these two terms and take integral from negative infinity to positive infinity. But we know that the PDF is equal to 0 around this interval, so the integral is limited to this interval. And we know that eta x means expectation x. Expectation x, we know that expectation x is equal to this value. We replace this value for expectation x and then compute this integral. And the variance is equal to this value. Okay, so this is an example to compute the expectation of a random variable and variance of a random variable for continuous case. Here our random variable x is a continuous random value. Yes, sure. To compute the variance of x, we know that variance of x is equal to this. So, to compute the expectation of gx, x minus eta x to the power of 2 is our gx here. We know that this is equal to this integral. Okay, here f(x) is such this. Here we have fx. We know that PDF outside the interval between a and b is equal to 0. So this integral is limited to the interval between a and b. What's eta x? Eta x is expectation of x, and in the previous part of this example, we compute it as a plus b divided by 2. So we have this. What's the value of fx in this interval between a and b? In this interval, the value of fx is constant and it's equal to this. Okay? Here you can compute this to the power of 2 and take integral from each term and then compute this integral that will be equal to this. Okay, any question? Okay, so we talked about expectation of x or mean of x. In this slide, we talked about some properties of expectation. Also, we talked about variance of a random variable. We discussed that the variance specifies the dispersion of a random variable around the mean of that random variable. And we have some properties of variance. But this slide is also important. In this slide, we want to talk about sample mean and sample variance. What's the meaning of sample mean? Okay, if we have a random variable x and we have the PDF of random variable such as fxx, then we can compute the mean exactly, okay, from this integral. Okay, if we have a random variable x and we know the PDF of x, we compute this integral to precisely compute the expectation of x or mean of x. Okay, but in real situation, we usually work with the samples of a random variable. Okay, in real situations, we usually work with the samples of random variables. If we don't know the random variable x, we don't know the PDF of the random variable x, but we know many samples of these random variables. For example, n, we have n samples of a random variable. Previously, in plotting a histogram, we discussed about the samples of random variables. Okay, x1, x2, and xn is the samples of a random variable. For example, suppose that the random variable x is related to the weight of peoples in a town. Okay, if we sample from this society, if we sample from this society, for example, we measure the weight of n people in this society, n individual in this society, x1, x2, and xn are the samples of a random variable that's related to the weight of a peoples in a society. Okay, here, when we have samples of random variables, we can compute the mean very simply. We can sum the values of samples and then divide the results by n. We can use this formula, but this formula called sample mean because it's the mean, but a mean that is computed from the samples. Okay, we call this formulation the sample mean. It means that the mean that is computed from the samples from x1, x2, and xn. We sum these values and divide it by their number. Okay, this is sample mean. Also, we can compute sample variance from the samples. Okay, how we can compute sample variance? To compute sample variance, we know that the formula of variance is like this. So to compute variance, we need mean of x. So at first, to compute sample variance, at first we compute sample mean. We very simply sum the value of samples and divide it by n. When we compute this value, then we use this formula to compute the sample variance. It means that this formula means that we reduce sample mean from all samples, then we compute power 2, and then we sum these values and divide it by n. This is the sample variance because this is a variance, but it's computed from the samples. It's computed from x1, x2, and xn, that is our samples. The real variance, the exact variance, follows this formula and can be computed from this integration. But when we don't have the PDF, but we have only the samples of random variables, we can compute sample variance. Okay, in this slide, we discussed about sample mean and sample variance. That means the mean and the variance that are computed from the samples. Okay, any question? Well, this was the last class session. I hope the class was useful for you and that you all do well in the exam. Next week, please pay attention. Next week on Saturday at time 13 at Iran time, you will have a class for TA. You have a TA class next Saturday.
Thank you, Doctor, for everything. Thank you so much. Doctor,
You're welcome.
if you can upload all this slide on system, please.
Yes, yes. Okay,
Thank
sure.
you so much. Doctor, this session is the last session.
Yes.
As you know, we need some time to study hard for the final exam.
Okay. So we don't have class in the next week, and you have class for only solving some problems for you in the next Saturday.
Thank you,
Okay?
Doctor, so much. Doctor,
Next Saturday, Mr. Feroz Murad is your TA.
Thank
Okay?
you so much. Thank you.
Next Saturday at the time of this class, you have TA class. Okay? Next
Thank you so
Saturday.
much. Thank you.
You're welcome. You're welcome.
Thank you.
دكتور
Doctor,
السلام عليكم.
can
I useful for you and that you all do well in the exam. Today,
Okay.
unfortunately, I don't have time and I have to leave the class as soon as possible.
thank you,
Okay,
Doctor. Thank
several minutes. We want to talk you if you don't mind, Doctor. Already you talking always, and you never let any person to talking only with the lecture. So now it's finished. So can I call Doctor? Just ask you. A lot of a problem we have now in the last two lectures. You already got to give us the exam for when you read the lectures with the law or the rule. You